All right, we are initiating an NC-AT-AET synthesis on direct current fundamentals. We're operating under Project Ampere protocols, which means maximum information density, no time wasted. So direct current, in our world, in aeronautics, it's absolutely mission critical. You're talking about the primary power for your emergency buses, the very thing that guarantees flight control continuity if you lose main power. It's also the fundamental language of the digital logic gates inside flight management computers. And on a component level, it's what forms the internal regulated voltage rails for all of our critical line replaceable units, our LRUs. Let's get down to basics. The reliability of any avionics system, and I mean any of them, comes down to the quantum-level characteristics of its conductive materials. If you want to do advanced diagnostics, understanding this stuff isn't optional, it's non-negotiable. Take a look at the copper atom, atomic number 29. Now, its electronic configuration is what makes it so special for us. An argon core with a 3d10 4s1 structure. The entire reason we use it for virtually all aviation wiring comes down to that single 4s1 valence electron. See, it's way out there in the outermost shell, and because of that, it has an incredibly high probability of just jumping into the conduction band with even the tiniest bit of electrical stress, what we call electromotive force. So everything really boils down to the valence electron count. It dictates a material's entire function. On one hand, you have conductors. They have 1 to 3 valence electrons, which means they have extremely high electron mobility. Why? Because their valence and conduction bands are practically overlapping. It takes almost zero energy to pop an electron loose and make it a free charge carrier. Now, on the other hand, you have insulators. They've got 5 to 8 valence electrons, creating a huge energy gap. We call it the forbidden gap between the valence and conduction bands. This gap actively resists electron movement, and that's what gives them their electrical stability. Okay, so we've talked about the physics of electron behavior. Now we need to put numbers to it. We're moving into the precise mathematical quantification of all this, the core electrical quantities. Electromotive force, or EMF. Think of it as the quantitative pressure needed to move 1 amp of current through 1 ohm of resistance. On the aircraft, you're going to see this generated in a couple of main ways. Mechanically, from your alternators and generators, or chemically, from your lead-acid or nickel-cad batteries. This force, this EMF, is the potential difference that really drives the current through the entire electrical architecture of the airframe. Now here's a number for you, 6.28 times 10 to the 18th. That's how many electrons are in 1 coulomb of electrical charge. But you have to make a critical distinction here. A coulomb is a static measurement. It's just a volume of charge, a fixed quantity of electrons sitting there. The ampere, on the other hand, is dynamic. It's a rate. It measures how fast that charge is actually moving. So, an ampere is the displacement rate of 1 coulomb per second. The classic marbles in a tube analogy really works well here. Imagine a tube packed with marbles. You push one marble in one end, and another one pops out the other end, almost instantly. That's how current works. For every single electron that enters a conductor, another one has to exit at the far end pretty much instantaneously. Now, what's crucial to understand is that this isn't about the speed of any one electron. It's about the speed of the propagation of the electromagnetic wave. And that concept is absolutely vital when you start troubleshooting high-speed data bus signaling. Okay, the ohm. That's our SI unit for electrical resistance, the inherent opposition to current flow. You calculate it with a formula R equals rho times length over area. That little symbol, rho, stands for resistivity, and it's a constant specific to the material. For copper, that value is 1.72 times 10 to the negative 8th ohm meters, and you better believe that value is fundamental. It's what you'll use for wire gauge selection and all your voltage drop calculations, directly referencing FAA AC 43.13-1B. Now let's talk power, measured in watts. It's the rate of work done when 1 amp flows under the pressure of 1 volt. So P equals I times E. Everyone knows that. But for us in avionics, its derivative, P equals I squared R, is absolutely paramount. Why? Because this is the formula for thermal management. It tells you exactly how much power is being dissipated as heat inside a component. And let me tell you, excessive I squared R loss is a primary failure mode. It's what leads to thermal runaway in semiconductors and the slow death of passive components. Heat kills electronics. All right, moving on to circuit laws and topologies. I need to be crystal clear about this. Ohm's law and Kirchhoff's laws are not some abstract theory you learned in a classroom. They are the immutable, governing principles that create the framework for all avionics circuit diagnostics you will ever perform on the flight line. Let's compare series and parallel circuits. In a series topology, you've got one single path for current. That means current is constant everywhere, and your total resistance is just the sum of all the individual resistances. The big drawback, an open anywhere kills the whole circuit. Now, contrast that with a parallel topology. Here you have multiple current paths. Voltage is constant across every branch, and your total current is the sum of all the branch currents. This right here, this is the fundamental basis for all modern aircraft bus design. It allows for an individual system to fail without taking the entire bus down with it. Next up, Kirchhoff's voltage law, or KVL. Simply put, the sum of all voltages in a closed loop has to equal zero. This is the absolute foundation of loop analysis. In any series circuit, KVL demands that your source voltage must perfectly equal the sum of all the individual voltage drops across your loads. If you measure and find a deviation, you've found a failure. It could be a high-resistance short or a load that's starting to go bad. And the counterpart is Kirchhoff's current law, KCL. The sum of all current entering a junction has to equal the sum of currents leaving it. This is the core principle behind what we call nodal analysis. Out on the flight line, you're going to use this to hunt down phantom loads or current leakage in your parallel bus architectures. It's simple. If the current going into a main bus junction doesn't match the sum of the currents being drawn by all the known loads, well, you've got an uncommanded path to ground somewhere. You've got a leak. So we've covered the laws. Now let's move from the abstract to the physical, flight-certified hardware that these laws govern. And when we talk about hardware, component selection is always dictated by stringent military specification standards, MIL-SPEC. Let's talk about the capacitor. It's a passive component, two conductive plates separated by a dielectric, designed to store energy in an electrostatic field. But its primary functions all come from one core property you have to remember. It blocks the steady flow of DC, but it passes AC. This single characteristic makes it absolutely indispensable for things like power supply filtering, signal coupling, and building the precise timing circuits that all digital avionics rely on. The formula for energy stored in a capacitor is W equals 1/2 CV squared. Notice that V is squared. That means the energy storage capability is quadratically related to the voltage. Double the voltage, you get 4 times the energy. We leverage this powerful relationship in high-energy systems like the aircraft strobe power supplies you'll find in ADT Chapter 33. We take these large electrolytic capacitors, charge them up to a very high voltage, and then discharge them in an instant to deliver the massive burst of current needed to ionize the xenon gas in a flash tube. Now look at this data for the 2N2222 NPN transistor. What this table reveals is a classic engineering trade-off, size versus robustness. On one end, you have the military-grade JANTX variant. It comes in a hermetically sealed TO18 metal can, and it shows superior power dissipation, 1.2 watts, and the lowest thermal resistance. Now compare that to the tiny SOT23 surface mount package. Yeah, it's smaller, but it has significantly lower power handling and much higher thermal resistance. That makes it incredibly susceptible to solder fatigue when you put it through thermal cycling. This all ties back to MIL-SPEC screening levels. The required system integrity, as defined by FAA AC 43.13-1B, is what dictates the component screening level you have to use. At the bottom, you've got JAN level, which is fine for non-critical systems. Think interior lighting. Step up to JANTX, and now you're talking about 100% power and thermal burn-in testing. This is what's required for something like a primary flight display. JANTX adds an internal visual inspection for components going into high vibration zones. And at the very top, you have JANS. This is the highest level, requiring full traceability, and it's reserved for space-grade applications like satellite comms. So, the final objective here is to synthesize everything we've just covered. We need to turn all this theory into a coherent, practical diagnostic protocol that you can use for troubleshooting line replaceable units on an active flight line. Let's look at how DC technology integrates into real aircraft systems. Take a Garmin G1000 system. The GIA 63 integrated avionics unit is a critical node in that system. It takes the main 28-volt DC bus from the aircraft, and then internally it uses these high-efficiency switching regulators to convert it down to the stable 3.3, 5, and 12-volt rails that it needs. Those rails power the GPS receiver, the VHF transceivers, the main flight guidance processor, everything. So a single failure in just one of those internal DC to DC converters can cascade into a total loss of both your navigation and communication capabilities. It's a critical point of failure. So here's your transistor switching verification protocol. It has to be systematic. Step 1 is a static test with the power off. You're going to do a diode check on the base emitter and base collector junctions. You should see about 0.7 volts forward biased and an open loop reading when you reverse the leads. If a junction is shorted, you'll read near 0. If it's open, you'll get an open loop reading in both directions. Simple. Step 2 is the dynamic test with power on. You probe the base, and you're looking for a base emitter voltage of about 0.7 volts. That confirms the transistor is biased on. Now, step 3 is the most important part, the collector state check. If the transistor is on, the collector voltage must drop to its saturation voltage, VCE sat, which is typically around 0.1 to 0.3 volts. If that collector voltage stays high, stuck at VCC, you've got a failed open transistor. All right, here's your final synthesis problem. You're troubleshooting a circuit with a JANTXV-N222A driver transistor. Your meter shows a base emitter voltage of exactly 0.7 volts, which tells you it has the correct forward bias. But the collector emitter voltage remains high, stuck at the supply voltage, VCC. The relay it's supposed to drive isn't clicking. So here's the question. Is the primary failure an internal open junction inside that transistor? Or is it possible you just have insufficient base current to drive the transistor all the way into full saturation? Your diagnostic reasoning from this point on will determine your next logical step. Think it through.